Good morning, ladies and gentlemen. Thank you so much for attending this session. We had a quick look at the count. It looks like we have 65 registered attendees so far, so we are winning in terms of score in the first breakaway sessions. However, I think you guys have made a poor decision. We're going to bore you to death. Just joking. Hopefully you'll find this insightful. So we'll be discussing supply chain network design decisions using open source tools. Before we get into that, just a little bit about who we are. My name is Llewellyn Steyn. I'm a supply chain advisor at DSV. I'm an industrial engineer by profession. And we are part of the supply chain optimization team in South Africa. We do a lot of similar things to what Joakim's team does in Denmark, and he'll elaborate in a minute. But in addition, we look at inventory optimization and simulation modeling and some other tools as well. Joakim, would you like to just quickly...
My name is Joakim Kejser, and I head up the analytics team in our supply chain optimization department in Copenhagen, Denmark. And we're a team that advise some of our customers on how to optimize their supply chains with a specific focus on transport and logistics, because that's what we do. We do a lot of network studies, we do a lot of transport optimization studies and the like, and that's some of the stuff that we'd like to talk about today.
Okay. So before we get into our topic, just a little bit about DSV. And there's two reasons I bring this slide up. The first one is the obvious reason. We like bragging about who we are as DSV. We're one of the largest logistics companies in the world. In terms of market position, we're third in the world in terms of air freight, sea freight, and trucking in Europe, third as well. And a little further behind in terms of logistics solutions, warehousing solutions globally. So we always like showing this slide. The second reason I bring this slide up is our perspective today is specifically from a transport and logistics perspective in terms of how we design our networks. So it might not necessarily be applicable to all businesses. Perhaps if you're in agriculture or very production-heavy business, some of the principles we'll be discussing today might not be that relevant to you. So I just want you to bear that in mind when we go through this presentation. So we'll be discussing three main topics, or sort of subtopics. The first is the importance of strategic network decisions, why network design matters, and some of this might come across as common sense, but I think as supply chain professionals, we need to remind ourselves of the importance of network design decisions. We'll then look at sort of traditional tools for network modeling and their dependence on data. And I think you'll gather as we go along that data is a really, really important aspect to making good network design decisions. As the saying goes, garbage in, garbage out. And then Joakim will take us into the open source tools that him and his team have developed in Denmark, that we use within DSV to make a lot of our strategic decisions with regards to network design. He'll elaborate on what our tool does and also what it doesn't do, and that's the important things we'll be covering there. So, the importance of strategic network decisions. So the business landscape is constantly changing. I think this is something we are becoming more and more familiar with over the last couple of years, and therefore we need to rethink our supply chain networks and redesign them. So why is it beneficial to redesign and optimize your supply chain networks? So there's sort of four main areas I want to focus on. The first is cost. So we are post-pandemic. We've got war in the Ukraine. We all know what the fuel prices are like. Consumers are under pressure. They have less spending power at the moment. Cost is going to become a crucial driver in our supply chains. We have to reduce cost. And one of the key ways that we can reduce cost is by redesigning our networks and optimizing our networks to reduce cost. And I think this is probably particularly from a South African perspective, but possibly in Europe as well.
From a European perspective, yes.
Cost is going to be a massive driver in redesigning our supply chains. And there's a lot of fat to be cut out of supply chains by actually looking at the network as a whole. Customer service. So this is a common one for us. Customers are increasingly wanting shorter lead times. E-commerce is still relatively new in South Africa. I think there's still a lot of growth in e-commerce, but customers want very, very short lead times, and that means that we need to be closer to our customers. So this is something we get a lot when we do network studies. How can we actually maximize our network in order to improve our service levels and get closer to our customers? In South Africa, often that would involve moving DCs away from the coastal areas. So we have a lot of urbanization in South Africa, as you know. Our economic hubs are more and more concentrated in around Gauteng, Cape Town, Durban. And moving our DCs to those areas allows us to get closer to our customers. The third one, environment. 5 years ago, environment would have made it onto the slideshow. It would have been on the list, but I would have just skimmed past it and just checked the box. But that is not the case anymore. We are, from a DSV perspective, increasingly under pressure from our customers, not only to report on the carbon footprint of our networks, but to actively involve the carbon footprint in our optimization strategies for our networks. It's becoming a key driver of network redesign and optimization. And I think that is something that's definitely going to keep happening, and it's going to become front and center in terms of network design and optimization. And then the last one, risk. And I think as South Africans, we understand the risk aspect very well. I only need to mention the riots in Durban last year, the floods this year, to understand that risk and mitigating risk and managing risk in your network is a key part of designing an optimal supply chain network. Okay. So those are the sort of strategic network decisions, the drivers of those decisions. I'm quickly going to look at some of the triggers, some of the events and symptoms that we find within our businesses that lead us to redesigning our supply chains. And we've in particular highlighted those top two, capacity requirements and network design that hasn't been reviewed for years. So we have internal and external triggers for network design and optimization. Those top two are the ones that we most frequently encounter from our customers. So capacity requirements would be a common one. You start off as a small business, you get to the sort of size where you have a warehouse, you have one warehouse, and as you rapidly grow, you want to add additional warehouses, and the question then becomes, where do you add those warehouses, and how big should they be? And that's typical capacity requirement question that leads to a network design. I want to linger on that second point a little bit. Network design haven't been reviewed for years. I think as supply chain professionals, we often make the mistake of not reviewing our network designs frequently enough, right? If we review network designs on an ongoing basis, and the tool that we have allows for that, and Joakim will elaborate a bit on that, if we review our designs frequently, means we can make small changes rapidly, instead of leaving a network for 10 years and then realizing that you have to redesign it in order to reduce cost or improve service. And then you have to go through a massive exercise. You have to employ a bunch of people to do the design. You have to move warehouses, move service providers. It's much better to frequently review your network than to let it get stale and old and have to revisit it. Some of the other internal triggers, I'm not going to go through all of them. Frequent use of backup distribution channels. So if you are air freighting things often, that might raise some eyebrows and lead you to wanting to redesign your network. Rising inventory levels is another good example. Inconsistent supply chain service levels. If you are consistently disappointing your customers in terms of service, that might be a good trigger to look at your network and see how you can improve your service in that regard. Mergers and acquisitions, from a DSV perspective, this is something we understand quite well. Mergers and acquisitions are a big part of our growth strategy. Every couple of years, we go through mergers and acquisitions. And post that process, we always have a process of consolidation. And as part of that consolidation, we need to redesign our internal networks. And that is often a trigger for us to look at our own distribution networks as well. And then new product launches and terminations. On the external side, changes in political and economic environment. I think I've touched on this before. Economically, things aren't going great, and you might have to right-size your network to accommodate for those changes in the economic environment. Regulatory changes in supply or demand. I think a good example of this is the automotive industry that's moving towards electric vehicles. I think we expect that to disrupt our supply chain significantly. Batteries inherently require different types of supply chains. Changing demand patterns, and then the last one, disruption of current supply chain nodes. And I think I only need to use one word there, and that would be COVID, which has really disrupted supply chains all across the world. So I'm quickly going to talk about tools for network modeling and the dependence on clean data, what the traditional tools are that we use, and why data is so important to network design decisions. So traditional network modeling tools are linear programming tools, and they are traditionally discrete optimization tools. And what we mean with discrete is that we specify the search space for the model. We tell the model what the options are. And inherently what that means is if you give the model a wide selection of options based on good data, the answer that you're going to get from the model is going to be of a high quality. If you give the model a poor selection, a limited selection based on poor data, you are going to get a poor quality answer. So the options the model is given defines the playing field for the model. If you do not give the model a lot of options or simply lack the data to do so, how valuable is the model actually? And the question you then have to ask yourself is, can you actually afford to spend time on gathering the right data so that you can give this discrete model the right options? And is that data even available? Do you even have the data and the resources to feed that into a discrete optimization model that will give you an optimal design for your network? So just to sort of show you some of the data requirements for optimal network design problems, this is a small example. The first thing you're going to need to know is, where are your customers, right? Which sort of seems like an easy question to answer. Of course, we know where our customers are, but we often find address data, and it's terrible, terrible quality. And often you literally get to this step of the process and you are bogged down. If you do not have good address data, understand where your customers are, what sort of weight and volume you're shipping to them, what sort of revenue you're generating from them, you can't even begin with some of the most basic network optimization models. The next thing you're going to know, or need to know, is where do you possibly want to build all your sites? Now, for a moment, I think we need to take off the South African hat here, right? In South Africa, we build DCs in Johannesburg, Cape Town, Durban, East London, basically, right? But if you put on a bit more of a global hat, you might sit, like Joakim does when they model in Europe, with 100 different options of where you can build a DC. For each one of these options, you need to understand what the location is, what the fixed costs are, what the capacities are at those particular locations, bearing in mind that these locations might be spread across different countries. So you have different regulatory frameworks for each option, different labor laws, for instance, and it becomes quite tricky to gather all of that data in order to input this into your discrete optimization model. Once you've done that, okay, if you even get to this point, you now need to understand transport costs. And you need to understand transport costs from each potential location to all of your customers. You're sitting with a massive matrix. You might have 2,000 customers and 50 different site location options. It becomes computationally a big data source to gather. All right. And the problem then is, do you have all of this data? And if you don't, do you even have the time to get all of this data? Your manager told you he wants a network designed by next week, Wednesday. Okay, it's not going to happen. And that really is the challenge with optimal discrete models for network design and optimization. So this is the trade-off. On the one hand, you have a large playing field, right, with limited data, all right, unless you're very lucky. If you do have all of the data, then by all means, use a discrete optimization model and you'll get the optimal answer. But the other option is a limited playing field where you can actually go into lots of detail and you can actually create scenarios for your models. And that really is where our open source tool heads towards. And I think Joakim's going to take it from here
I'll try.
and
at least.
inspire you.
No, so I'm just going to tell you a little bit about why have we chosen to implement some of this in Python as well, and how we use that to do center of gravities and a little bit more, and how we use that to support strategic decision making or network design decision making as well. And I think I just want to start out by saying what is the general approach to doing some modeling, whether that being network design modeling or just general optimization modeling. There's always a start out with some data, whether that's Excel or a CSV file or it comes from an extract of an ERP system or something. We have some data that we need to work with. We need to clean that data, make sure that it fits into whatever modeling tool that we're using at the end of the day. You could use Excel for that. A lot of people do that. Maybe you're a bit more over on the data science wave and use Python or R, or you use a fancy extract, transform, load tool with a good user interface or something like that. Then you need to model it. That often comes in a separate modeling tool. And then after you've done your modeling and run your models, you need to compute some statistics or visualize it. And maybe the modeling tool can do that, or maybe you load it out to a business intelligence tool or Excel or whatever you think is the right tool to use here. The issue with this approach from our perspective is it's difficult to be rapid. It's difficult to do a lot of stuff because you go in and out of different tools and does it fit together? Is it the right format and all of that? So that was what led us to think that we use Python already to do a lot of data analysis and cleaning and working with data in general. Could we just stay there and not move out of that ever to do a lot of our modeling? So based on that, we implemented a few things in Python, and I'll get in a bit more into detail with some of them, but we implemented geocoding tools so that we can turn address data into coordinates quickly and efficiently. It sucks to sit down and type all of that into Excel and upload it on some website to get the coordinates back. That's too cumbersome, right? So we use all the APIs of Google Maps and all of that, but we can do it all from Python and query it that way. Then we've implemented a lot of different center of gravity models, and I'll get a bit more into them on the next slide, but it's really to do location choice models and answer location choice questions and compute statistics that are not cost-based that we can compare these networks on. And then we have made some visualizations tools to make it look pretty and appealing, because that's very important when you have some impatient stakeholders that need to look at this stuff. What we've done from the center of gravity perspective is we've gone two routes. We have the simple stuff, as we call it, that's the continuous models, and we have a little bit over in the discrete side that Llewellyn also talked about. For the continuous ones, these can answer questions like, where should I place P warehouses, and what are the optimal locations for them? We don't have to specify locations up front. It will place warehouses in the continuous space, and it will use only as the crow fly distances, right? So this means that we could rapidly do stuff. We don't have to specify a lot up front, but it also has a few downsides that it can place locations in the middle of the ocean if you're unlucky. Or we can not further constrain the models to do more cool stuff. But it's really quick. We'll show you a few examples in a bit. Then we have the discrete models, where we do have to specify all the possible locations that the model can choose from up front. But we can also do cooler things, like we can specify different distance constraints. So that could be road distances instead of straight line distances, or it could be cost if we wanted to give the model that, or lead time, whatever. That doesn't really matter. And we can put a lot of additional constraints on them. That means that we can ask different questions to our models. So we can ask questions like, I want to cover 95% of my demand within 500 kilometers, assuming that that's a good distance. How many warehouses do I need, and where should they be? We can also ask other questions like, I want to place one additional warehouse. Where should we place that to maximize the amount of demand I cover within 500 kilometers? So instead of coming and saying, we want 2 warehouses, we ask the model instead, how many warehouses do we need to meet some sort of business need? Of course, it's still rather high level, 500 kilometers, where did that come from? That's an assumption that you can maybe drive 500 kilometers in a truck in Europe in one day. So we still have to make those assumptions. Is it 95? Is it 100%? How much of your demand do you really need to cover? But that's the stuff we can play around with and get a lot of different results. So how do we really use this, also compared to the traditional way of modeling all the costs and everything that Llewellyn alluded to in the beginning as well? How do we use them in network modeling? And we do 2 things. We do simple network assessments. So those are the ones where we get some data and we clean it. We can never get around that. Then we do the center of gravity modeling. We can do a few different scenarios, and then we simply just compare network statistics. And again, we'll show a few examples, and that's it. But that's a rapid thing we can do. Is my network still looking good? I know we built it a year ago. Demand has changed a little bit. Are my locations still in the right place? So. Right? That's a good and healthy check to do. We also use it in a bit more elaborate fashion. A lot of stakeholders and decision makers would like to see business cases at the end of the day and not just fancy slides that look pretty. So same approach, we get the data, we clean it, but we start out by building an SS model. We don't do that in a modeling tool as such, but we take the data and we cost that with up-to-date rates and lead times, and we always get up-to-date rates and lead times because we're trying to compare networks and not your 2-year-old contractual rates with up-to-date rates today. It needs to be the networks that we're comparing. Once we've done that, then we use our tools again under the 2B modeling, so we use them to generate scenarios. So we run these models, we talk to the customers, what is it that you'd like to achieve with this network? What are the lead times that you require towards your customers, at least so, and how much do you need to cover? And based on that, we can compute a lot of different scenarios that we use as input to a workshop that we have with the customers, where we go through what are the right scenarios for you based on our logistical expertise as well, but also based on your knowledge of your business. You're the expert on your own business, right? And based on that, we can shortlist a set of scenarios that then we can cost in a similar fashion as what we did for the SS modeling, and then compare it in the end. So the downside of this particular approach is that it's not true optimization as such, because then we needed to gather the cost for all the possible options that we have in the network and cost all of that. But to Llewellyn's point early on, we just struggle to get all that data, and not just to get it, but also get it in a consistent fashion where we're not comparing rates or bad quotes or something with each other, but we're comparing networks. So in terms of pros and cons of the traditional tools and the open source tools, I'm not going to say open source tools in general, but at least what we've tried to implement with our Python tools here is the pros is it's free, so you don't really need to pay a huge amount of money for it. It's quite customizable, so we can get it to do more or less whatever we want it. And then I think the most important thing for us right now is that we can piggyback on the whole data science tools wave that are out there, right? So we heard about AI and machine learning a little bit in the beginning today, and a lot of that is going into Python and some of the other programming languages out there that we can piggyback on. And then it allows us, because we keep everything within one tool, we can really rapidly do some of these analysis if we are provided with somewhat decent data. In terms of cons, I mean, it's a steep learning curve. There's no fancy user interface and drag and drop, so we need to teach our engineers how to use these tools by actually writing some of the code themselves, right? And you never know whether the models are actually implemented correctly. There's not a big brand out there saying that this is the right way to model your supply chain. That is the engineers who are building these models that do that. In terms of the traditional tools, I mean, you do get well-established tools and well-established training programs for this specific use case, right? You do get true optimization, so if you do have the data to specify the whole network, then this is the way to go, for sure. You can really get true optimization that way. And then they do not only provide a tool, but they provide an established optimization framework to model various issues in your supply chain that you don't just get by default in some of the open source tools out there. In terms of cons, and maybe we're biased, but it requires a lot of clean data, and it's sometimes quite elaborate to set up a model. So again, if you get that case that Llewellyn mentioned in the beginning that somebody wants it on Monday, right, then you're going to be a little pressed for time. Lastly, I mean, some of them can also seem like a black box, and that's something that we preach to the analysts in our team as well, is that you must understand when you type stuff into the models, how does the results differ from what you did before? And if you don't understand that, then we have a fundamental issue. Then it's just a fancy optimized tool, and then it gives you a result, and you blindly trust it. There was a lot of talking from our side, but I think we just want to show a few examples as well, what output we can kind of get out of our tools. So the first one here is just a random data set of data across Europe, and the size of the dot kind of indicates how much demand we have at each customer location. And what we just try to do is to show you how does the network develop as we go from 1 warehouse to 10 warehouses, because it looks very pretty as well. We start out by putting a warehouse in the Netherlands, at least that's what the model suggests. And one of the interesting things of being able to do this rather quickly is we can also compare what if you had 3 or 2 or 5, and how is that going to impact your network and your growth aspirations over the coming years. Because the interesting thing that happens now is if we want 2, all of a sudden it's in the northern part of Italy and the UK. So if you place that first warehouse in the Netherlands, now you need to move things around if you want to have that additional warehouse, or something has to be in a suboptimal location, right? We do 3 warehouses. Oh, now we're back in the Netherlands, so maybe it was good enough to begin with anyway, and you could have expanded upon it, right? I'm just going to go through the rest of them quickly, but it just splits the demand as we go along, right? Parts of the geographic regions will just be split. Of course, we struggle a little bit with this, that it looks nice and we can show that to stakeholders, but how do you make decisions just based on looking at the maps as well? That's difficult. So you need to understand some metrics that we have behind the network that we can use to compare these different scenarios with. So what we do as well is we try to compute the weighted distance. So the weighted distance is just the amount of kilometers you drive, how much demand or how much weight or whatever you use to model in your network. And it's not perfect, but it's a pretty good proxy for your transport cost at the end of the day. And that's what we use it for. And what we see down on the x-axis down here is the number of locations that we just went through, and then that weighted distance up. And we see that when we go from 1 warehouse to 2 warehouses, that not halves, but it drops significantly. From 2 to 3, it also drops significantly. From there on, it kind of tapers out. And the additional benefit, at least in terms of the driving distance you have to your clients, get a lot less as you move on. So even though we don't know the cost of this network, we could at least tell ourselves that as you go beyond 4 or 3 warehouses, you need to have good reasons for why you want to do so, because it might be expensive in terms of warehousing. The other perspective of it is, what about my coverage? How much of my demand am I covering within a certain distance, if that's important? If it's not just a cost supply chain, but a supply chain where service is very important towards the customer. And here we just show how big a portion of your demand is covered within a certain distance that we have down on the x-axis here. And then we have it for the different scenarios with 1, 2, and up to 10 locations. And again, we see that the first one, for about 500 kilometers, we cover 60%. If we have 2 warehouses, we're all the way up at 85%. And then from there on, the benefit of adding additional warehouses are not that great, at least from a holistic network perspective, but maybe for a smaller geographic region, it could improve. And then I think Llewellyn just included some pretty slides of South Africa as well, so everyone can relate. All right. So here, it develops as to be expected, as I'm told. So we start in Joburg, we get down to Cape Town as well, 1 in Durban, 1 in Port Elizabeth, and then from there on and out, smaller locations in this particular network. And the last example that I want to bring you today is just one where we play around with these discrete models instead, because we can ask some way more interesting questions to the models. But here, as we alluded to, you need to first specify what are the options that the model can choose from. So we can't just say choose from anywhere in Europe or anywhere in South Africa. We have to specify the options the model can choose from. So in this particular case, we've just taken all cities with more than 250,000 inhabitants and say you can choose from that. Those are likely good locations to be at. What we then just try to do and say, what if you needed to cover 80% of your demand within a set distance? How many warehouses would you need? Because the funny thing is we have a lot of clients that come to us and say, we need to cover all demand within 1 day. We say, okay, then you need a lot of warehouses. And when we then compute it for them and say, okay, you need 20. Then they say, oh, but we have 2 today. We can't have 20. And that's just more powerful than having the initial discussion with them. To make it even more interesting, we can also do it if we say, what if we needed to cover anywhere between 80 and 99% of demand within a certain distance? What happens to the number of locations that we need? And just like the other graph we saw, I mean, if you want to be within a very small distance, you're going to need a lot of warehouses, and then it drops off rather quickly. We've chosen just a few to show you how the network actually develops in terms of, on the map. So we'll show some 500 kilometers and 1,000 kilometers examples here. So if we need to cover, we're looking at the same data set as we did before, but if we need to cover 80% of our demand within 1,000 kilometers, we need just 1 location, and it will be where we saw the center of gravity was before as well, in the Netherlands. The colors on the map indicates how close the customers are to the warehouse. So green is 500K, and yellow is 1,000, and then so on. If we then want to cover 95% of our demand, then we're forced to have 2 locations. So we're adding 15 percentage points, but we need 2 locations to cover that much. And if we want 99, only 4 additional percentage points, all of a sudden we need 3 warehouses to be able to cover everything within that 1,000 kilometers. So is that worthwhile, those extra 4 percentage points worth an extra warehouse? If we go down to 500K, then it's even more elaborate. So 80% within 500 kilometers, you actually need 3 warehouses. 95%, you need 1, 2, 3, 4, 5. And then if you need 99%, I mean, you need a lot of ridiculous warehouses. So this is where we have to interpret our models a little bit as well, right? But it will do what we tell it to do, and that is cover 99% of demand. But I don't think, even though it would be nice to visit, but I don't think we need a warehouse down in Sicily, even though I'd like to go. So in terms of takeaways, these were the examples we wanted to show you, but we also just want to reflect a bit and give you a few pointers out of this session before we take questions. And that is, we think it's important to review the strategic network decisions often. It is a lot easier to do some of the more high-level stuff, and you can get away with doing some of the high-level stuff if you do it often. Whereas if you leave it be for 10 years and you have a very established network or warehouse structure, you need a very, very solid business case to convince someone to move it. Minor adjustments are easier in anticipation of change than those reactionary adjustments that you need to do afterwards. And then, of course, we need to have that opinion, but take supply chain data quality serious. I mean, you need it to make good decisions. That's just how it is. And people regret it afterwards, and you can't do anything about it afterwards. You need to do it going forward, right, and make sure that you have the data available. Then we encourage everyone to consider at what level of detail do you want to, but also can you model your supply chain. So if you don't have all the good data available, then don't come asking for a very elaborate model and all of that. Think about what can I actually do with what I have available. That's going to affect the tool choices and the modeling choices quite a lot. And then lastly, there's a lot of smart tools out there, what we've made and all the classical ones, but we think the people who actually use them are the most important ones. And if you have a tool and you use it once a year, you're not an expert in that. You need to use it repeatedly. So we would always recommend hire smart people, hire people who can build this sort of stuff and use it to the best extent. That's way more important than the tools. Yes?
Thank you.
We got about 5 minutes for questions, thanks to Llewellyn and Joakim. I think that was great. So yeah, any questions from the audience? I think put up your hand. Yeah, we'll bring a mic. I don't know if there's another one at the back, but let me just do a walk down.
Hi, Jeremy Baskin from New Ways. Thanks for that presentation. Really good to see how quickly you can model the different networks and distribution centers. But one of the key things when you're doing this model is inventory and cash and stock. So every time you put in an extra distribution center, effectively you're taking your inventory and timesing it by 1.3, 1.4, as well as the factors as service level. So how do you build that into your model?
We don't build it in upfront. And that is an inherent flaw, and you're absolutely right? We would consider that afterwards in the scenarios we try to generate, and we will use our knowledge of that exact thing to make sure that we consider both scenarios with a few warehouses where we can aggregate stock, and also several warehouses where we can try to get that benefit of being closer to the customer at the cost of additional stock, right? If you really want to model everything up front, you have to go back to maybe some of the traditional tools. But it's back to the question that can you truly model all those choices? When you start talking about inventory, it becomes quite detailed, right? And you need even more fine-grained data to be able to do so. And can you get that into the model up front? That's then my question. But we consider it afterwards, yeah. I don't know if you have anything to add.
No.
Okay. Any other questions? Here we go. Thanks.
Hi, I'm Rajiv. Question regarding how would you bring in the suppliers and their kind of supply chain and lead times and their locations into this model, into your analysis? Thanks.
Super valid question. Today, this is mostly focused towards the customers as well, so towards the distribution like that. You can add your suppliers in as demand instead, and just include them as well. The issue is you'd always have a more efficient inbound supply chain than you do in an outbound supply chain. So how are you going to account for that in your models, right? But we are working on making additions to those discrete models as well, where we can add suppliers in there and make sure that their supply gets distributed through the network and then account for it like that. But it is an inherent flaw with a lot of those center of gravity tools, that how do you correctly include inbound volumes or suppliers in the network. But yeah, we try to do that. We often do it by adding it in and say, what if we weigh them 25%, 50%, 75%? Then you kind of get a line towards the suppliers as well, and then you must be somewhere on that line. But that's just often not as specific as we'd like it to be.
Yeah, in South Africa, if you add your inbound volume, you move your warehouse from Joburg to Pietermaritzburg. It's essentially what happens. So.
Yeah, we always move it towards the major ports in Europe as well, be that Hamburg or Rotterdam or something like that, especially if it comes from overseas, or if you're a big air freight importer, then towards one of the major airports, right? So if we find a center of gravity, and unless you have a lot of different suppliers, we know that you're somewhere along that line between the port and the center of gravity that we've computed, right?
Great, thanks. I think we've got time for 2 more questions. Any other questions? There we go at the front.
Hi, I'm Krish Govender. The question I got for you is clean data, because the quality of data you put in is what is the quality you're going to get out. And we find that a lot of times when we download data, we have to scrub the data to get it to a certain point of cleanliness. What have your guys done to ensure you get clean data, that you don't have to do so much of scrubbing of your data?
I'm afraid that we're more the receiver of the data than the ones deciding on how good it's supposed to be in the future. But we do spend a lot of time on working on it. It's simple things as inconsistencies in data that really gets to us, right? So the same city is spelled 7 different ways. You might think that that's simple to fix, but it takes a long time to figure that out in the data. So we're trying to use some of the fancy data science tools out there to compare city names and all of that to clean it up. But fundamentally, that doesn't fix the problem, right? I'd like to get the clean data in the first place. And I don't know if, I think we're on a journey where people need to realize the value of having that clean data. That goes for our own company as well. We're not perfect. We also struggle with data quality sometimes. But certain stakeholders here and there think that it's more important to do things quickly rather than having the right data quality, right? And that's what we'd like to change. But whether I have the final solution for that, I don't think so. Do you have anything to add?
No, I think the tough thing is often the data comes from the customer. You need to find the right way to push back to the customer. Even on our courier business, we have massive address data issues, and most of that is from our customers, and we need to politely tell them, to improve their data quality so we can improve our service to them, and that's often a difficult conversation. So data quality is not a problem that's going to go away anytime soon, I'm afraid.
And the issue with these sorts of studies are that it's not something you do often, right? So it's not, you can say, let's improve the data quality for the next one we're going to do. Maybe that's 5 years down the road or something like that. And once you get to doing the study, it's too late to fix the data quality issues, right? And telling people why that's important, because 5 years down the road, you might need to make an important decision. That's difficult. Yeah.
Good.
Sorry, last one. I'm James Tubb from Barloworld. I guess the thing here is that you've started with an open source tool, but what you've done with it is very much proprietary now.
Yeah.
So what is actually the benefit of using the tool off the shelf versus developing it in terms of the cost and the outputs of them?
That's a good question. You do get something that's more established, right? So you're very reliant on people if you want to do this yourself, right? And hence the point of hiring smart people. On the other hand, the tools out there, they're not just something you give to someone and give them 5 hours and then they're up to speed and they can do whatever you want in them. They're also quite elaborate, right? So just because you buy a tool off the shelf, you'd still need to invest a serious amount of time in your people to learn how to use that tool. So that would be the benefit, that there are then training programs available for them out there that they can go on, right? And there are peers to talk to about this that are not working on some proprietary software, but they are working on something that you can also get trained in, right? With that being said, I mean, a lot of the models that we've implemented, any industrial engineer can also go implement. The math behind it is not necessarily particularly complex. It's the way that we have tried to integrate it into the rest of the stuff that we use to make that efficient. I think that's the benefit to it more than it is the actual models. The models are way more sophisticated in the off-the-shelf solutions out there.